All right. So the objective of today is to actually start programming Gaussian elimination. You know how to work on a problem by hand. Last time on Friday, we have actually learned how to set the problem up. So how to actually come up with a linear system that solves an engineering problem. Okay. So most likely than not, maybe in some small cases you will come up with a 3x3 or a 4x4 or a 5x5 system. But even 5x5 is not something that you want to deal with by hand. So you do actually want to program your solution. Now, for solving systems of linear equations, you can actually get to MATLAB and you can just solve it in MATLAB, fine. But the point of this class is to actually show you how do you develop an algorithm, especially if you have to specialize it in some sense for your application. How do you actually develop an algorithm on your own so that you're more independent in the work and that you also know how to assess whether the program is working correctly. So I will basically review the Gaussian elimination and specifically the part that was probably a little too abstract when I was writing it down in class. But that abstract part is actually going to help us come up with the rules how to program this. Okay? So, and then today you will actually work on programming a Gaussian elimination. So let's just go back quickly to the slides, just as a general review. A lot of engineering problems, and some of them we've seen on Friday, you basically set up as a system on n equations in n unknowns. There could be also different setups where you have less equations than you have unknowns, so then you know that you have multiple solutions and not just one. And then basically Gaussian elimination is a systematic algorithm that helps us solve those. So what we had as it was a two-step solution. In first step, we were doing so-called forward elimination. So we were systematically picking a pivoting term. So yeah, I start with element A11 and use that element or that row to replace any row after that with a linear combination, appropriate linear combination of the, for instance, I will going to replace second row with a linear combination of first and second row that will eliminate A21, that will make it 0. Okay? And I'm going to then move on to the third row, and I'm going to replace the third row with a linear combination that makes A31 eliminated. Once I'm done with that, I move on to so-called second pivot, A22. Okay? And then I'm going to use second row to eliminate A32 in this case. And I'm going to keep moving on. Again, the point of using this is not a 3x3 system that you can solve by hand. The point of using this is in a larger system that you're not going to attempt by hand. Once you're done with that procedure, okay, you end up with an upper triangular system. And this upper triangular system has zeros below the diagonal in my matrix of coefficients A. And I'm going to use so-called back substitution to calculate my solution. So in this particular case, this last equation is very simple. It's U33 times x3 is equal to d3. So obviously my x3 is just d3 divided by U33. Okay? So once I have that solution, I can plug it in here, and I'm going to have a very simple equation for x2. Then I'm going to solve for x2, and I'm going to keep moving up. Okay. Now, what is the challenge in programming this? When you're doing things by hand, you kind of obviously, the human brain is very good at recognizing patterns. But for computers, we have to actually write down those patterns in a very specific way, or else computer will have no clue. Okay? So you will automatically say, oh yeah, of course, I plug in x3 into this equation and I just plug it in. But if you want to write a for loop that does that for you, then you have to formalize those steps and write an algorithm. And that's going to be the hurdle in solving these problems. Like you know how to describe things in words and you know what to do in a 3x3 system, but now you need to go and take it one notch further and make an algorithm that will work with the n-by-n system. Okay? And it can be done, but it's a little bit of work. Recognizing that pattern, formalizing it in terms of for loops that need to run to actually solve this. Okay? So that's going to be the challenge here. So we actually did a little bit of work that, I think it was before here, right? So basically this was actually the formalization of those coefficients, and you might have it in your notes as well. So basically we actually went, what I will do here in replacing the second one, I will take this coefficients, and I call this coefficient A21 over A11 times this row minus the first row. Okay? And that will kill this first number here. So I can recognize it's A21 over A11. When doing the same thing for the third row, it's going to be A31 over A11. If I had the fourth row, it would be A4, the coefficient would be A41 divided by A11. So I can see the pattern and I can try to program it. Okay? And this for loop, I'm going to have a for loop that will go and work on row by row for all of the rows below this first one. Okay? And then I'm going to move over. So this is my first pivoting term, right? So for this first pivoting term, A11, I'm going to, in a for loop, eliminate all of the coefficients below it. They go from 2 to n, and n being the number of rows. Okay? And then I'm going to move over to the second term, pivoting term. I'm going to call that A22. We called it A22 tilde, but I'm going to just replace things in the matrix, so it's still going to be A22 in my program. And then for that one, I'm going to run a for loop for all of the elements below. And I'm going to move over and work again the same. So I actually have a nested for loop. I'm not sure if you see it right now, but if you start writing down on a paper, you will. So what I want you to do is I want you to go and basically either work from these slides or write it down or however you want it. These are the slides that were posted. And you also go download on Canvas. Let's see if I still have it open. Probably not. Canvas. On Canvas in MATLAB, I posted a shell of a code. Files. You go to Files, go to MATLAB. This is where I'm posting most of the stuff from the class when we work on things. So you can see bisection was posted in this. And there's this solve linear system class. I'm just gonna double check that that's, that'll do. So download that. I'm just gonna put it. And I'm just actually going to just say solve linear system. I'm going to name it solve linear system. And now I will open it in MATLAB. What you see me do, by the way, cd is a change directory command, so I can actually type in to change directory as long as I know the full name of the directory. Or you can just click on things on the left-hand side. Now I'm a bit of an older generation than you are. These clickables were not available when I was studying, so I'm still actually used to changing directory by hand and moving over. What's useful with these is that you actually could have it as part of your script, okay? Because clickables you can't program. This is actually programmable. So if I was setting up an entire workflow to go to a certain directory, or even create it and whatever, I could all program it here in MATLAB. So just have that as a possibility in your brain. Now, those of you who actually, how many of you have Apple computers? So Apple computers are Unix. Do we know what Unix is? So Unix is an operating system, and it's different from DOS, which is the base of the Windows machine, a Windows machine. So those are two different types of operating systems. The main difference in computing, and this is why I'm telling you, is that Unix machines are capable of networking much better than the Windows machines are. So typically for most of the Windows machines, you have to have one person logged into the machine at a time, whereas the Unix-based systems actually allow multiple users to log into the machine at the same time, which is helpful in parallel computing. So large-scale computing, you will typically have shared resources where multiple users will actually log into the same machine and work on it simultaneously, and they can do so. So Unix is the environment that allows that. And basically, Apple took Unix as an environment and built off of it. There's also so-called Linux. Has anybody heard of Linux? So Linux is a free operating system, so anybody can download it and compile it and so forth, and it has quite a vibrant community of developers, so everybody can also contribute. So those are different modes of operating systems that you might actually encounter in your career as well. Again, it's slightly different, it's nothing that you couldn't tackle, and those of you who have there's this terminal, I have it on my dock, but you can actually find it in the utilities where you can actually do the same. You can change directory and move around as you can. And you can find the command window as well in DOS, which is this operating system, which is base of the Windows, but the command will be slightly different. So this is a little bit of a tangent just to explain what I'm doing here. So I'm not doing any magic. I'm just typing in commands. So this is actually now I'm in the directory that I need to be in. And I'm going to open this solve linear system. I changed the name of this. So I'm actually just going to, you will have it, if you change the name, you will have it underlined because it should be the same as the name of the file, solve linear system. And I have already put the shell of this, so some helpful things and hints, and you will just add to them to actually solve the problem. So for one, I actually have a little help here. So it's going to be function x is equal to solve linear system of a, b. A and b are my natural inputs, okay? And your assignment is that for matrix A and vector B provided as an input, you want to solve AX is equal to B. And there are some initial checks that are already provided down in the file. I also provided and what should you use to check whether your program is working correctly. And this is something that we'll solve in class. This is one of the first examples we solved. So in your step 1 here, I'm just making sure that input parameters are of correct size. So basically, if I'm checking that my matrix is square, so I'm specializing just for square matrices. And if it's not, it's going to display an error message and sort of return an empty vector. Okay? If also my number of rows of A is different from number of rows of B, okay, then I don't have matching A and B. So I'm going to have a trouble there as well. And I'm just going to return an empty X, which I call trivial here. Okay, so those are the initial checks so that you have some checks in place. And basically I have now, step 2 should be forward elimination. Okay. So you should work on forward elimination just as suggested. And three of us will move around and help out. And then you will work on backward substitution. So I already, n here is not programmed, but n should be the size. So I'm going to program it right now so you can type in with me. So n should be this size of A1. So that's the number of rows and number of columns as we check. And then basically there's x. I'm setting it as zeros. And I'm setting this very last element that we know from backward substitution. And the rest, you should be able to program how to get the rest. And I'm giving some hints here and help. Okay. Any questions before you start working on this? It is very helpful to have a piece of paper and write things out, even if you're using the slides. Would it be helpful to leave this slide on? Yeah? There's this slide. I think I had some in notes. You can discuss with your neighbors, you can work in pairs. Just be sure that you are actually working on the problem because you want to understand this, you want to know how to do it. And let me see. So this is actually from my notes as well. So this is from notes of the 30th. And this is the slide, so whichever is helpful. So I'm actually going to pause the movie here.